Welcome to The Explainer. You know how Netflix just knows what you want to watch next? Or how a business can somehow predict next quarter's sales? Well, a lot of times the magic behind that is a really powerful tool called regression analysis. Today, we're going to decode a pretty standard statistics assignment to show you exactly how this thing works.
It's a classic question, right? Businesses, scientists, you name it, they're all trying to figure stuff like this out. And very often, the key to unlocking an answer lies right here, in the statistical method we're going to explore.
So, we're going to take what looks like a few homework problems and turn them into a clear story. We're going to show you exactly how to build one of these predictive models, and, just as important, how to figure out if it's any good.
All right, let's jump in. Here's our game plan for today. First, we'll get to know the prediction machine. Then, we'll meet the key players. After that, we'll see how to measure a single prediction, give the model's overall performance a grade, and finally, we'll learn how to read its full report card.
So at its very heart, a regression model is really just a prediction machine. And, like any machine, it's built from a blueprint. Only in this case, that blueprint is a mathematical equation. This equation right here, taken straight from our source material, is our machine. It's actually really simple. You feed it a number for x, it does the math, and it spits out a prediction. We call that prediction y hat, or y hat. That little hat on the top just means, hey, this is the predicted value. Okay, so we've seen the machine. Now let's pop the hood and see what makes it run. See, to work, every prediction machine needs an input and an output. And that brings us to the key players in our model. First up, you've got the response variable. Just think of this as the main event. It's the thing we're actually trying to predict. So in our examples, that could be lumber sales or monthly salary. It's the effect we're interested in. And on the other side of the coin, you have the explanatory variable. This is the cause, or the input we feed into our machine. So think about it this way. How much we spend on advertising is the input we use to predict the output, which is sales revenue. It's what we think explains the change. Okay, so our machine made a prediction. It spat out a number. Great, but was it a good one? Was it even close? To find that out, we've got to compare our guess to what actually happened in the real world. We measure this accuracy with something called a residual. I know, it sounds a little technical, but it's really just the error in our guess. Think of it as the leftover. It's the difference between what our model predicted and what the real result was. So let's actually do this, using the first problem from our source. Step 1, we grab our equation. Step 2, we plug in our known x value, which is 10. That gives us a predicted y of 7. Then, for step 3, we compare our prediction of 7 to the actual real-world value, which we know was 8. So the difference between the actual value, 8, and our predicted value, 7, is, well, it's 1. That's it. That's our residual. It's our error. And here's the really crucial part. The sign of that number tells us which way we were wrong. A positive number, like our 1, means we guessed too low. We underpredicted. If that number was negative, it would mean we guessed too high. Simple as that. So measuring one error is useful, but that's like judging a whole movie by watching one scene. It doesn't tell us how the machine performs overall. For that, we need a grade for the entire model, and that's where something called R-squared comes into play. To get that overall grade, statisticians use this thing called an ANOVA table. And I know it looks kind of complicated, but don't worry. For what we need, we just have to focus on a couple of numbers here in the SS, or sum of squares column. You can just think of these as telling us how much of the story our model explains versus how much is still left over as an error.
The math is actually super easy. You just divide the regression number by the total number. So that's 555,420 divided by about 2.5 million. And boom, that gives us our R-squared value, about 0.22 or 22%. Now this is what R-squared actually means, and it's pretty cool when you see it this way. It tells us that our model, just using an employee's length of service, can explain about 22% of why salaries are different. But that means the other 78% is still a total mystery. It's unexplained by our simple model.
So this leads to a super common question. If we want a better grade, a higher R-squared, can't we just keep adding more explanatory variables? Just keep throwing more stuff into the machine?
Well, not so fast. There's a catch. Regular R-squared will almost always go up when you add more inputs, even if they're totally useless. That's why we use adjusted R-squared. It's a much smarter metric that actually penalizes the model for adding variables that don't really improve its predictions.
And as you can see here, Model 1 wins because it has the highest adjusted R-squared. Okay, let's put everything we've learned together. We're going to take a look at a full report for what's called a multiple regression model. That just means it's one with more than one explanatory variable. This final table really brings it all home. Here, we're trying to predict lumber sales using two inputs, housing starts and commercial construction. These coefficients here are the new numbers for our machine's blueprint. And look at that R-squared, 82%. That means our model, with just those two factors, can explain 82% of the variation in lumber sales. Now that's a pretty powerful prediction machine.
So, let's do a quick recap. We've learned that a regression model is basically a prediction machine. Its inputs are the explanatory variables, the cause, and its output is the response variable, the effect. A residual? That's just a single prediction's error. R-squared is the model's overall grade, and adjusted R-squared helps us pick the best model when we have a few options.
But this brings us to one last and honestly, one of the most important points. Our lumber model can explain 82% of what's happening. That's an A+ grade. But does explaining something automatically mean we've proven a direct cause and effect relationship?
The answer to that is a hard no. And this brings us to maybe the most important rule in all of statistics. Correlation is not causation. Just because housing starts and lumber sales move together, our model doesn't prove that one causes the other. And that is such a critical reminder that even the best models are just tools. They still need careful human thought to be interpreted correctly.